So how is data sent? Now I'm going to give an overview of digital communications. Now here are the four main blocks in what's needed to transfer ones and zeros, which are stored in the memory of either of a computer or a digital mobile phone, for example, into something that can be transmitted over the channel. And let's think about what that means. And so I'm going to give examples for each of these main blocks to explain what they are. Let's start with the channel. I always like to start there. It's a physical challenge that's there from nature. We need to find a way to get these ones and zeros into a form that can be transmitted. And so how do we do that? That's our challenge. So let's think about that channel. In the frequency domain, we can see that there are two main types of channels. This is the frequency domain. And one of the types of channels is what we call a baseband channel. And I'll just draw this here that says that these frequencies pass through the baseband channel and higher frequencies don't. And examples of these are things like unshielded twisted pairs, for example. This is what ADSL, VDSL is transmitted over, for example. It's also the channel that I'm using right now to communicate with you, my voice channel. So we can make noises and voice signals up from about a couple of hundred hertz up to about 3,000 hertz, 3 kilohertz, and that's in this baseband channel here. So this is a form of communication, me talking. Let's think about how we look at and get some signals from data over these baseband channels. Another channel is what we call a passband channel, and that operates at what we call a carrier frequency. So this is where you've been allocated an amount of bandwidth around a carrier frequency, and you need to send your data through that channel. So what does that mean? That's what we're going to look at briefly here now. Okay, let's think about what the sorts of waveforms are that exist in these channels. So at this frequency here, this is in the time domain, we think of a type of signal that's a sinusoid. So the signal that's exactly at the carrier frequency, if I was to think of that in the time domain and do samples of that and plot it, it would look like a sine wave at that carrier frequency. So we need to transfer our ones and zeros into some sort of waveform that can be transmitted over time that looks like this, that has these kinds of oscillations at these frequencies so that it goes through that channel. If we're thinking about this channel here, well, signals that go through there are much smoother, much lower frequency, much smoother signals. So for example, my voice in time depends on the scale that you look at it, of course, but a slowly varying signal like this is something that exists at lower frequencies. So it's good to have these pictures in our mind when we're thinking about the physical challenge of getting the ones and zeros through the channel. So let's work backwards from the channel then, and let's think about how we're going to do this from ones and zeros to these types of waveforms. We call that modulation. So one thing that we're going to have to do for modulation is we're going to have a digital to analog converter. So I'm just going to draw this here as a digital to analog converter. So that's going to convert ones and zeros into a signal. For example, I'll draw a signal that might be coming out of a digital to analog converter. It's in the time domain, and it might be a signal like this. It might go up from 5 volts, for example, a voltage, let's say 5 volts, between 5 and 0. And the 5 volt, while it's at 5 volts, the output of the digital to analog converter, while it's at 5 volts, it might represent a digital 1. While it's at 0 volts, it will represent as digital 0, for example. This is one example. So now we've got coming out of our digital to analog converter, and what's inside here is electronics. We won't go into all those details, but there's plenty more you can learn about digital to analog converters. But at the output, it's important that there's a wire coming out of the digital analog converter circuitry, and on that wire, the voltage is changing between different levels. And it's now a time domain signal. So this thing transfers ones and zeros from discrete data stored in memory into a waveform in time. That's a crucial concept. Okay, now we've got to transfer that into something that can go through one of these channels that looks like one of these kinds of signals. So let's think about the most probably basic way. Let's think about 3 different types of channels. I'll just give 3 as examples. So let's look at a type of channel called an unshielded twisted pair that we talked about here. So this is standard sort of telephone line channels. Unshielded twisted pair. Okay, so what we need for that, well, again, that's just some wires. They happen to twist as they go for interference purposes, but they're just wires. So I'll just draw that with a line there. And what we need to make sure is that the voltage or the power going down into that onto those wires is going to be enough so that it can get without too much loss along those wires and get to the destination at the other end where the receiver is. So for this, we need an amplifier. So that's an amp. So for the unshielded twisted pair channel, it's as simple as this: a digital analog converter, we're talking about the modulation box here, to give you a signal like this, and then an amplifier which amplifies that to the power level that you're going to use for transmission. And on these wires is this exact signal, just with the power that you need for the task that you have, for the distance you need to transmit it for. So this is the most basic type of modulation. I'm just going to look at 2 others to give a bit more insight. Let's look at an optical fibre. So if we had an optical fibre, again, I'm just going to draw that as a line because it's just one fibre. What we would need to go into that fibre, of course, is something that churns this signal here that comes out of our digital analog converter into light. And so this is a laser. So we put our signal of 1s and 0s into a laser. This is one way of doing it, where we basically turn the laser on to represent a 1 and turn the laser off to represent a 0. And then the signals coming out of that laser are going to look like these type of signals here. Let me just draw that here. Again, in the time domain, it's going to look like a burst of light oscillating at the frequency of light, followed by nothing for the 0, followed by the burst of light, and so on. And so you can see this signal here looks like this one over here. It's going to be in the pass band where FC for the laser is the frequency of the light that you're using to send in your optical fibre. So here again, we're going from 1s and 0s stored in memory into a waveform in time, where we're going from 2 different levels from the digital analog converter. Then we're going to put that as the input to a laser, which is going to turn the laser on and off. And it's going to cause a signal like this to come out of the laser, where these oscillations are at the frequency of light that you're going to be transmitting into the optical fibre. And when you turn it on and off, it has the effect of spreading that frequency, like I've shown here, to have a frequency range around the basic frequency of that light. And there's plenty of videos on that on the channel, and you can find in the description, in the link in the description below. The third one, so this is called on-off keying. So just on-off keying. It's a basic idea of a type of modulation. I'll just give one last because it's a very common one, and people are always interested in it, of course, and that's when we're using a radio frequency channel. So what if we have wireless communications, such as mobile communications or Wi-Fi? Well, of course, the thing that we need there, we don't have a cable of wire or an optical fibre, but what we need, of course, is an antenna. We draw that like this. So we have an antenna as the thing that's going into the channel. It's radiating from an antenna. So what we need before that, of course, is an amplifier, just as we did before. In this case, the laser has the effect of the amplification. So you can modify, let me put a line through this laser here. You can make the laser brighter or dimmer, and that affects the power. That's how you control the power. Whereas here we need an amplifier, which is again electronic circuitry with transistors and op amps and so on, and they connect to the antenna, and the antenna then oscillates the electromagnetic wave. The frequency coming out of here causes this to radiate, and that's how it goes into the channel. Okay, so we've got an amplifier, and of course, how do we turn this 1s and 0s into something at that frequency? Well, we do that with something which we call a mixer. So I'm just going to put the word mix here, and of course, there's more information elsewhere. We're just doing a summary today. Okay, so these are 3 different examples of what happens in a modulation box so that you can send a signal over a channel at the frequency that you're interested in, either a radio frequency, this might be 2.4 gigahertz, for example, for Wi-Fi, or an optical frequency, where this is the frequency of one of the colors of light, or it might be this frequency here, a lower frequency, where it might be an unshielded twisted pair cable, maybe, for example, on the first generation of Ethernet, or serial bus lines on a motherboard of a computer, for example, are all using this low pass bandwidth. So this is modulation. So this is really the key to changing ones and zeros into a waveform where it can go over a channel. So what are these other two boxes? Channel coding and source coding. We definitely have ones and zeros coming through here. This is a sequence of ones and zeros in here. What are these two other boxes doing for us? Well, what is going to happen in our channel is we're going to possibly have errors. So when it comes to our receiver, when our receiver receives these waveforms, I should draw this waveform here, of course. Let me just go one example further here for this waveform. So instead of on-off keying, we often use something which involves the phase when we've got radio frequency, because our receivers can receive the phase accurately. Whereas for optical fibers, the receivers that we have generally, or the ones which are able to be put into commercial grade consumer products, can't estimate the phase of the light. So, but you can estimate the phase of the radio frequency. It's a lower frequency, and we have receivers that can estimate the phase. So in this case, what we can do in our mixer, instead of just multiplying straight by this signal here, we can do some other things where we can encode the data into the phase. And I'm just going to draw an example here. So for a 1, we might send a positive sine wave, and for a 0, we might then send a negative sine wave, and then for a 1, we send a positive sine wave again, and so on. And so this is, and this waveforms here are at the carrier frequency of our Wi-Fi. So for example, this might be a waveform at 2.4 gigahertz, and there'll be more cycles than I've drawn, but I'm just drawing this number for simplicity. But in this case, we're encoding the data into the phase, and this is called phase shift keying. So we had on-off keying and phase shift keying. These are another different way of sending ones and zeros. Okay, so coming back to our challenge of what these boxes are, well, when they go through the channel, these signals can possibly be received at the receiver end in error. So there's always going to be noise in the receiver from thermal noise, from all the electrons moving in the receiver amplifier. I haven't drawn the receiver chain here, but there's an equivalent set of boxes which mimic these but happen at the receiver to do demodulation, then channel decoding, then source decoding. And so at the receiver, where the signal through the channel has received with small amount of power, for example, in radio waves, the energy radiates in all the directions but is only collected at the receiver in one of the directions, so the signal is received weak. And so there's potential for noise and for errors to be made, and that this was not then decoded back to a 1. It might be that noise causes the receiver to decode this as a 0 by mistake. So to help us with that challenge, this is the box of channel coding. So channel coding, what channel coding does is it introduces redundancy into our ones and zeros stream. So we still have a ones and zeros stream, but we are introducing redundancy so that if errors happen in our channel, at the receiver we can work out that those errors happened and hopefully correct those errors. I'll just give you one example of channel coding here to give a bit more practical insight into this. I'm going to talk about 4/5 rate parity check coding. So we'll just call this 4/5 rate parity, and I'll explain what that means here briefly. So let's say our data input stream here was 0, 1, 1, 0, 0, 1, 0, 0. Let's say, for example, this is this data stream coming into our channel encoder, the data stream we would like to transmit. If it's this, in 4/5 rate parity, what that means is every 4 bits that come in to be sent, we're going to send 5 bits out of our channel encoder. So we're going to send more data out here than comes in, but the extra data we add is going to help us overcome errors in the channel. That's the purpose. So let's say, for example, if it's 4/5 here, so there's 4 bits here, what we're going to do is introduce a 5th bit. We're going to introduce it as either a 0 or 1 so that when we look across those 5 bits, we see an even number of 1s. So in this case, 0, 1, 1, we've already got an even number of 1s, so we're going to insert a 0 into the data stream. After these 4 bits, we're going to insert another bit in there, and it's going to make sure that those 5 bits have an even number of 1s. So currently they've only got 1 1 in them, so we're going to have to insert a 1 into the data stream. And so this is what we call 4/5 rate parity checking, because parity refers to an even number of 1s, and 4/5 means every 4 bits we're going to introduce a 5th. So the output rate here is higher than the rate here because we've only got the same amount of time to send the bits, so we've got to send them faster here. We've got to send them 5 on 4 faster, okay, than here. But what it means is at the receiver, if this data stream, the longer data stream was received, and if, let's say, an error happened here and a 0 was received here instead, then at the receiver it would look at those 5 bits and it would see 0, 1, 0, because an error, 0, 0, and I think, there's not an even number of 1s, so an error must have happened. So in this case, you can detect single errors that happen. And in more sophisticated versions of channel coding, you can actually identify where the error happened, which one of the bits was in error, and you can then correct those errors. We won't go into all that here, but that's the purpose of channel coding. It introduces redundancy in such a way that it helps you to detect and hopefully correct errors that happen from the channel. So that's this channel coding box. And the last box to talk about is source coding. Let me talk about that. So what's source coding doing? Well, source coding is doing almost the opposite of channel coding. Source coding is removing redundancy. The difference is source coding is removing the redundancy that you don't need to send because you can work it out already at the receiver. Whereas channel coding introduces redundancy that we know about, that we do need to send because it's going to help us to correct for errors. So what do I mean about removing redundancy that doesn't need to be sent? Well, let me give one example. And this is an example that is similar to the GIF in encoding. So if you've got image processing and you know about GIF images, of course, then this is very similar to what happens in GIF. Let me use that as an example. So if you had let's say a cartoon image and it had a lot of one color, it was just because cartoons often have constant colors then just with the lines of where the cartoon characters are. So let's say this was let's just think about white and black for the moment. So let's just think if, for example, if there were, if this is an image and we're going to look at the first row of the image, okay? And so let's say, for example, the first 128 bits were white. And then let's say the next 128 bits were black. So let's say those pixels, so let's say instead of bits, pixels, but we've got to send those pixels and we've got to send a lot of white pixels and then we've got to send a lot of black pixels, for example. So let's say this was, let me just do it, let me do another one here. Let's say we had 256. So this is pixel 255 is the last one here, and then let's say this is pixel 511. So it's fully 512 long, and let's say that was the width of your image, 512 pixels. Starts at 0, so we go to 511. What we could do is we could send 512 zeros, sorry, 256 zeros, 256 zeros, followed by 256 ones. That's what we could send to send the first row of that image. But if we know that we're going to get long runs of a single color followed by long runs of another color, then we can actually compress this into a shorter sequence. So this is 512 long, this sequence, and you could send the data like that if you wanted to send the raw data. But instead, let's say we use another encoding. Let's say our encoding says, pick a block of where they're all the same and give the bit, say that what the bit is that tells the color, and then let's say we're going to allocate 8 bits to represent the length of that run of that color. So in this case, we've got 256 is the length of the run of these zeros. So we could allocate these 8 bits to 256, and in 8 bits, 256 is 8 ones. So in binary. So we've got 1, 2, 3, 4, 5, 6, 7, 8. So if we had 8 ones follow this, what this would do is just tell us, okay, we're dealing with the color white, and we've got 256 white pixels in a row. And then the next, then we just follow this. We could use this technique continually. So the next block of pixels is a black block, and then also it goes for 256. So 1, 2, 3, 4, 5, 6, 7, 8. That's another 8 bits to say that the black lasts for 256 pixels. And in this case, we're sending exactly the same information for the first row, but we're only doing it with 19 bits. So here we needed 512 bits, but if we use this type of encoding, we only need 19 bits. And so 19 is obviously a lot less than 512. So this is one example of source coding where you are able to compress the digital signal of ones and zeros into a smaller length of ones and zeros. You're still containing exactly the same information. You haven't lost any information at all in doing this. You've just been clever about the way that you are storing and recording the information, and you're doing it in a smaller number of bits, which means that your communication system is going to be more efficient. So there's obviously other ways that are lossy, that are even more compression, such as MPEG, JPEG, MPEG for images and for videos and so on. And there's links in the description below that tells you what the ultimate limit is, and that's an information theory concept called entropy. There's also an information theory concept about the channel coding, which tells you the maximum rate you can transmit or the maximum rate you can have of this channel coder for 0 errors. And that's called capacity. And those are 2 information theory concepts. You can find information in the links below. So hopefully this video has given you more insights into how ones and zeros are sent over channels. And of course, it's just a summary, but there's lots more links in the description below with more details of many of the components. If you've found the video useful, please give it a thumbs up. It helps others to find the video. Subscribe to the channel for more videos. And as I said, you can check out the description below. You'll find the link to a web page which has a categorized listing of all the videos on the channel.